everyone, welcome to the lecture 11 of course Climate Change and Extreme Events. In the previous lecture we have talked about different types of probability distribution functions, and we have also talked about what are their applications in let us say climate science or data analysis, or if we have long record of climate or hydrological data set, how we can use these probability distribution functions to understand how the statistical property has been changed, or what is the statistical property of the data set. Then we have also talked about using these probability distribution functions, we can figure it out if there is a change in the system or change in the stresses because of the climate change or human activities like that, how the data behavior will also change in terms of statistical properties of probability distribution functions. Then we have also talked about in the previous class how we can use different types of probability distribution functions for different types of hydrometeorological extreme events processes, and then we can also use different types of parameter estimation method, for example, to fit the distribution into the data set, and then we can try to calculate what is the return period, return magnitude of different events, so that we can have a better understanding about what is their probabilities of occurrence and also what are their likelihood magnitude for different events. So, these information we have already covered in the previous lecture 10 of climate change extreme events. In this particular lecture, we will talk about extreme value theory, extreme value analysis and its applications. So, extreme value theory is basically centered around the extreme events which are very rare in the nature, but when it occurs it creates more catastrophe or more risk or more different types of socioeconomic problems because of these events. For example, large scale flooding or let us say long duration drought event or frequent drought event, for example. So, when you are saying these kinds of different extreme hydrological or hydrometeorological events, these has some sort of magnitude with some sort of probability of occurrences. Generally, when we are talking about extremes, which means the magnitudes are very high, or in the drought conditions, let us say very low, but probability of occurrence is very low in the natural settings. So, what we have observed in the past 30-40 years, different types of extreme events are continuously rising across globe, and therefore these extreme events are posing a significant amount of economical because of the damage these events are creating to different parts of the world. This is the representative figure which I have taken from NOAA, where this figure is actually showing the the cost in $1 billion of different types of extreme events. So, it suggests that if you look at the trend since 1980 to 2021 or 2020, it suggests that the trends are continuously rising and extreme events are occurring more frequently, and therefore it is causing more severe damage to the different socioeconomic conditions of different regions like that. Therefore, it provides it gives you more insight about why we should learn the extreme value, or why we should be aware of this particular topic, so that we can calculate their risk, to calculate their magnitude depending upon their different probability distribution functions, and depending upon what type of the data set we are collecting at different locations. So, in this lecture we will primarily talk about the fundamental of extreme value theory. Then we will also discuss about the key concepts and distribution in extreme value theory. Then we will analyze the EVT or extreme value theory or distributions applications in analyzing the climate extremes. Then we will also discuss about some of the tools which are useful in implementing different types of EVT model in climate data analysis. So, before moving into that more complex part of this presentation, first we need to understand about what is exactly extreme value theory. So, extreme value, as we have just discussed, is a statistical framework, is a mathematical framework which is used to analyze or model extreme events such as a record breaking temperature, intense storms or catastrophic floods. Or not only these extreme events, there are so many other events also. We can use the extreme value theory to model these extreme events, so that we can assess their probabilities and their magnitude of rare and high impact occurrences. So, this is exactly the definition of the extreme value theory, or the model which we use to get an idea about what is exactly the probability and magnitude of these extreme events. When we are talking about application of these extreme events, these can be applied in let us say annual flood analysis, severe storm prediction or temperature extremes analysis or review, or tail risk assessment, what is their the high end behavior or low end behavior of different data set, like that. To analyze these different types of extreme analysis, we have to break it down data into different parts. One way is we can break it down the data into peaks over threshold. We will talk about this in the later slide. And then another approach is called block maxima, which is also very useful technique to extract the extreme values from the time series data set and then try to understand what is their behavior based on different models. So, why it is important? Because it gives you a risk quantification. It can let us know about the return level prediction. We know that what is the magnitude of different extreme events at different probability scenario or return level. Let us say if you are talking about what is the magnitude of 100-year flood, or what is the magnitude of 50-year flood, or what is the magnitude of 100-year temperature extremes in a certain region, like that. So, these kind of the extreme quantifications or return level prediction we can assess. And once we have these kind of information, for example, let us say you have 100-year flood magnitude data at certain point, we can provide you can calculate what would be the inundation region based on that 100-year return period magnitude of flood, and then we can quantify how much the area likely to be inundated if that types of floods will occur. Therefore, this is basically can enhance the risk management strategies and can gives us a more insight about what is likely to happen in a certain locations or cities or districts, like that. So, so these applications we can do in wind speed analysis, flood analysis, heat wave predictions and drought assessment, and then we can have different types of understanding about these extreme value or extreme events based on different extreme value models. So, there are key concepts in extreme value theory, which is one of the very used term is called block maxima method. So, block maxima method is basically when you have, let us say, collecting the data in years or months, or let us say daily data for 365 days for 1 year. So, basically we try to find out what would be the maximum value in that maxima, block maxima, in that block. Let us say you divide your data into 365, 365, 365, that is 1 year. You say that this is a block, and in each of these block you try to find out what would be the maximum value of a particular meteorological property. For example, we are talking about annual maximum rainfall, where we are trying to analyze highest rainfall recorded each year. You try to collect the 365 values at one particular location, and then we will try to find out what would be the maximum value for 1 year. Similarly, you repeat this experiment for multiple different years. Let us say if you have 20 years data, that can generate 20 different 20 values for your annual maximum rainfall. What is the purpose of these block maxima is basically to identify the statistical behavior. You have now time series which represents individual years or individual, let's say, months, or what we are deciding the blocks, and then based on that block we can basically calculate the statistical behavior of the time series, and we can also calculate the extreme event probabilities. Once we have different data points, we can calculate what would be the probability of occurrence of different magnitudes, like that. Then another very commonly used terminology is peak over threshold. So, as the name suggests, peak over threshold. So, you draw the threshold, and whatever peaks occurs after that threshold is considered to be your maximum values, right. So, that is basically we have predefined high threshold or a certain threshold level, and based on that whatever the values are occurring in that particular year, you can get multiple values, and therefore, that is your sort of extreme values for that particular properties. So, in the peak over threshold method, generally generalized Pareto distribution methods are used when you are using the block maxima, where we can use the generalized extreme value distribution, GEV distributions. Suppose we are measuring the river discharge and certain flood stages threshold, and then we are trying to figure out what would be the river discharge after crossing this particular threshold. So, as the block maxima approach, here it also suggests that the extreme behavior of the data set, and also tells about what is their probability of occurrences. Generally, these methods are more efficient when we have smaller data set. We need to create multiple data points. The another very commonly used term is called return levels. Return levels are generally called when you are trying to find out what would be the magnitude of certain extreme events based on different time period or the return period. For example, if you are talking about 100-year, what would be the magnitude of 100-year flood? Let us say temperature extreme, what would be the magnitude of temperature extreme in the case of 50-year return period, like that. So, this is the return period. Generally, it can be calculated by either your block maxima approach, or you can use the peak over threshold method to calculate their return period. So, that is basically generally can be fitted the GEV model or data or distribution into the data, and then we can also fit the GPD distribution to the data and then calculate what is the probability of occurrence of different values. Suppose we are interested in 100-year flooding. So, if the data is distributed in block maxima or peak over threshold, we try to identify the particular model, and based on that we would be able to calculate what is their probability and magnitude of occurrences. So, this is very important because it is gives a risk of the rare events, high impact events, and it will also tell us about the infrastructure planning and risk mitigations, like that. So, this is a one graphical representation of block maxima and threshold exceedances. So, here suppose this is your first block, this is your second block, this is your third block, and this is your fourth block. Now, you look at it. So, let us say this is any particular extreme value quantity, and here you are measuring continuously. So, for the first block you have the highest value, that is called x2. For the second block you have the highest value, which is called x5. For the third block you have x7, and fourth block x11. Similarly, you have multiple different values. So, you record those values which are falling the maximum value in that particular block and then you arrange that value in such a way that it will look like a time series data set. In particular, when you are talking about threshold exceedance, here if you draw a threshold here like that, or one particular value, whatever values are crossing above this particular threshold will be your peak over threshold, or values above a certain thresholds, like that. So, what is the key difference in these two different concept is when you are using the block maxima, you will have a total number of values equal to the total number of years, because for each block maxima or total number of block maxima, like that. So, let us say if you have 100 maximum values, so it means that these 100 maximum values will be originating from 100 different blocks or 100 different years, based on whatever you are deciding for the blocks. But on the other hand, when you are using the threshold exceedance, it might not be the possible. It might possible that in 1 year you have 3 events, or in 1 year you don't have any events at all. So, it may not be possible in the threshold exceedance method that number of years is exactly equal to the number of events. It might possible in 1 year you have multiple events, 1 year only one event, or 1 year we don't have any event, like that. So, which means when you are using the threshold exceedance method, you have more probability of occurrence of more number of values compared to your block maxima approach. So, why we do these types of sorting of the data set? Because when we are sorting these types of data set, one thing we are keep in mind that the events which we are selecting for extreme value analysis and all, this has to be independent, not mutually dependent. Independent means, let us say if there is a high peak of flood occurs and subsequently next day there is another high peak also occurs. So, there is a highly likely possibility is that the second peak will be dependent upon the first peak in the process. For example, you have higher soil moisture and therefore, a moderate amount of rainfall can also create a higher amount of a higher peak, something like that. Therefore, when you are sorting the data in such a way, block maxima or threshold approach, we keep in your mind that whatever the extreme values we are selecting, it has to be independent in nature, and it has to be not dependent in any process representations, like that. So, in the beginning we have discussed about when we are talking about, let us say, block maxima approach, we generally use the generalized extreme value distribution. When we are using the threshold approach, we are using the generalized Pareto distributions. So, the GEV distributions are one of the model which are used in EVT, extreme value theory, where it is basically used to model the block maxima values which are we have collected from this particular method. So, there are 3 different types of these GEV distributions. One is called Gumbel, second is called Fitchett, and third is called Weibull. So, these are the 3 model within the GEV distributions which basically model the different types of annual maxima or block maxima values for different types of extreme value analysis. For example, we can analyze the flood risk, we can analyze the temperature extremes, we can analyze the precipitation estimation or annual maximum rainfall, like that. So, there are 3 different parameters which is very essential in our GEV distribution. For example, SAPE. SAPE is basically tells about what is the heaviness of the tail, whether the tail is more towards the positive direction or not very much in the positive direction, like that. So, if it is positive, then that particular distribution of the if the parameter is, let us say, eta parameter is positive, the GEV distribution tends to be the Fitchett distributions. When eta is equal to 0, then that is called the Gumbel distributions, where we have eta is 0. When eta is less than 0, which is negative numbers, the Weibull distribution we can consider. So, this is the property of the SAFE factor, which defines what type of extreme value distribution or GEV distribution can be fitted in the model, in the data set. Scale is basically the spread of the extreme values, and mu is the central tendency of the maximum values or maxima whatever you are collected from the block maxima approach. Then the second model is called generalized Pareto distribution model. This is called GPT. Generally, it is used for peak over threshold method. Peak over threshold method. Here basically we model the tail behavior, particularly the distributions and particularly the rare events, and then we are also using the SAFE parameter to identify different types of GPT distribution which are we are modeling or fitting into the data set. As similar to the GEV distribution, GPD distribution also used for flood risk assessment, drought analysis, wind speeds, like that. But here the main difference is we are using some sort of threshold. So here we have also 3 different parameters, that is SAPE, where we tell about whether heavy tail distribution or light tail distribution, or bounded extremes, like that. The scale parameters tells about the spread of the exceedance, and there is another parameter which is U, that is called threshold, which tells about what is the predefined threshold for that particular data set where we are fitting the GPD distributions. So these are the 2 models which are widely used for extreme value theory. But in the previous lecture we have also talked about, let us say if you have distribution, merely knowing the distribution is not enough, we have to fit into our data set. What is fit? Basically we need to find out the parameter of the distribution based on some sort of observed data record, right. So basically we can divide our data based on block maxima or threshold method, find out the data set where the data sets are not dependent with each other, these should be independent. Once we have figured it out the data, then we have selected one particular type of distributions, and then we estimate the parameters. Parameters means, let us say if there are 3 parameters in one particular distribution, it will be have some specific values, and that value will tell about the specific type of GEV or GPT distributions. Within the GEV, you will also will know that what is exactly the value of, let us say, eta parameter, whether it is negative, positive or 0, what is your scale parameter, or what is your central tendencies of the data of your distribution function. Once you have already defined these parameters based on our observed data set, we can basically validate our fit based on some sort of goodness of fit test. So there are 2 types of methods which are used to estimate the parameters in the from the observed data set or observed maximum values. There is one method is called maximum likelihood estimation, where it is generally less uncertainty quantification. It is basically used for large data applicability, and it is generally used for some sort of data driven parameter estimation. But on the other hand, we have Bayesian approach, where we basically focus on uncertainty quantification as well. Bayesian approach are generally used for when we have small set of data set, and we try to find out what is exactly the appropriate parameters values based on that small set of data set. And Bayesian approach also integrates what is the prior information about different types of parameters with the help of your observed data set. That is basically called the Bayesian approach, and based on these 2 different method, we can find out what is the values for your parameter. Once the values have been established, we can basically validate our model based on certain types of goodness of fit. So let us suppose we are using the maximum temperature data at one particular station, or let us say gridded data set of CRU. CRU is providing the the climate data set for global area, and we can use the data which is available at gridded format. Or let us say if you are using some sort of station based data set. So here you have 365 values or 366 values for individual years, daily values for maximum temperature. You try to find out what would be the maximum value for individual years, and then you make some sort of time series. So you can do this analysis for station based record also. You can do this analysis for your gridded data or CRU based data or reanalysis product or IMD based rainfall or extreme or temperature data set, like that. So once you have formed the time series of a certain station or gridded data, we need to check whether these data sets are stationary or non-stationary. In the previous lecture we talked about, we have to check whether the statistical properties are consistently changing. We need some sort of time varying model, or if it is not consistently changing, we need some sort of stationary models which we have discussed about, GEV, GPT or all these models like that. So, first we have to make sure that whether any stationarity should exist in the data set. Let us suppose our data has a jump suddenly in between in certain years. So, what we can do in that type of data set, we can divide that data from the jump, before jump and after jump, two types of data set, and we try to fit our distribution for one set of the data and second set of the data, and then we can compare. So, this way we can remove the non-stationary conditions, the changes of the statistical properties of the data set based on the dividing the data into two parts. So, we have to find out the stationarity test, then after the stationarity test we extract the time series. Then depending upon the length of the time series, either we can go with the peak over threshold method, or we can go with the annual maximum series AMS or block maxima approach. And based on these different approaches, we can find out GEV or GPD distributions, and then we can estimate the parameter, and we can make some sort of evaluation criteria whether the fitting was correct, or what is the parameter estimation has less uncertainty, more uncertainty, like that. Once this model has been selected, we can use for this model for different types of written level predictions. So, these types of models are generally used for, let us say, heat wave analysis, where we are interested in frequency and severity of temperature extremes. We can model the record breaking temperature using extreme value theory or Gumbel distributions, for example. We can talk about, let us say, wind speed analysis. We can make some extreme model to assess risk to structure and infrastructure, like that. We can also talk about flood analysis, where we can calculate what is the extreme probabilities of flood events using river discharge data or rainfall data set, or we can also calculate 100-year flood return levels and their probabilities and their magnitudes, like that. Or maybe we can use the drought analysis to understand what is their likelihood behavior, or what is their probability of occurrences, and what is their magnitude of low flows during let us say drought conditions, like that. So, these are the some of the applications when we have data set, and we can use different types of models to fit or to get the idea about different types of extreme events. Generally, the written level, where we are talking about the magnitude of different probabilities for the extreme events, we calculate that. Let us say if you have fitted the model called GEV, GEV quantile is calculated is the function of 1 by T mu sigma and eta. Mu, sigma and eta are the parameter of the the GEV model, and 1 by T is called the T is your probability of exceedance, the time return period. So, let us say if you are interested in 100 years, we will put here 100, 1 by 100, 1 minus 1 by 100, which means it is like 0.99. For that particular we will quantify the GEV quantile based on the selected parameter, and then we can get the magnitude of the flood. So, there are this is the one of the example where we have a return period, different return periods up to 100, and we have calculated the magnitude of different we know that from our empirical data set what is the return level based on magnitude based on different return period. Once we know these information, we can fit our model here in the case of GEV model, and then we can calculate what would be the profile or behavior of the data set. So, this kind of the analysis can be done by Python libraries, where we can use fit GEV model or calculate return levels, or some sort of R packages where we can also use some sort of fit GEV libraries where we can call them, and then that will fit the GEV model, and then directly can give us the return level estimate. So, suppose when you have fitted the model either GEV or GPT or Gumbel or VBIL or Fitchit, like that, we have to be make sure that whether your model is correctly behaving your empirical data sets or not. It is also very useful if you wanted to find out, let us say, whether your parameter estimation techniques gives you the accurate results or not, whether it is converged to the best parameter values or not, right. So, in that case we basically use the goodness of fit test where we a statistical test to evaluate how well the fitted EVT model represents. We basically assess the model reliability for predicting extreme events. There are some sort of tests like Case test or Anderson-Darling test, which are used to find out whether your fit is accurate or not. Some sort of graphical representation which is called quantile plots, where we basically use this plot to fit whether your empirical data set and your theoretical data sets are converging at one single point or not. Threshold selection, we are mean residual life plot, where basically we use these types of plots to identify the selection of the threshold in peak over threshold method is appropriate or not. Then we will also use some sort of return level plots, where we try to find out what is the return level magnitude based on different probabilities, and then we can compare this with our empirical data set, with theoretical data set, and then we can cross check whether our theoretical model, here theoretical model is your fitted GEV or GPT distribution with your empirical data set, whether these two data points, the theoretical and empirical, are converging at one particular line or not, like that. And then we can also calculate what is the uncertainty of this. What are the challenges in the EVT? Model validation is one of the challenge, because we have to be make sure about whether whatever the model we are selected or we have calculated the parameter, it has to be validated with our further record. Threshold selection is one of the very important criteria, because it can give us a more about what is their independence in nature, and if there is a low threshold, there will be too many points. If there is a high threshold, there is a fewer exigence probabilities we will get. Then we have to also check about what is the non-stationarity. It is very important criteria, because when we know that global warming is rising, or rising temperature, or CO2 rising, like that, we have to be make sure that whatever the extreme value time series we are using, it has to be some sort of stationary in nature, or if there is a non-stationarity conditions exist, we can detrend or we can break the data into several parts, so that we can analyze it into different distribution patterns, like that. And then we can also understand about the sample size, how many extreme events we have in the time series data set, and what would be their how we can use these data set for calculation of different return levels. So whatever we have discussed here in this particular lecture, it has to be we can replicate all these analyses into different libraries which are available in Python, R, MATLAB, and these are the softwares, EasyPattern and SAS. Here you have different types of libraries. We can use it to understand the parameter estimation, for example, return level in quantile plots, visualization of plots, goodness of fit results, and different types of model fitting and validation algorithm. And that can be used for multiple different types of extreme value climatic analysis for different parts of the world, like that. So in this lecture we have talked about what is exactly EVT, extreme value theory, and why it is very crucial for understanding and modeling the extreme events. We have also talked about what is exactly block maxima, what is exactly peak over threshold, like that, or what is exactly annual maximum series, for example, it's a part of block maxima. Then we have also talked about, let's say if you have time series with block maxima, then we have to use GEV model, where we have 3 different models, like that. Or if you have, let's say peak over threshold, we can use GPD model, and where we have some types of parameters we have to estimate based on maximum likelihood or Bayesian methods, like that. So these are the some of the very important models which are very useful in application of, let's say, flood risk, heat waves, and structural design in terms of when we are calculating the return period, return level, and their frequencies. So in tomorrow next lecture we will talk about how we can analyze the frequency and intensity of extreme events using some sort of probability distribution function, which we have already covered in the previous classes. Thank you so much for your attention.